Welcome again to our journey into the fascinating world of deep learning in artificial intelligence. In this unit, we will explore convolutional neural networks, or CNNs, the cutting-edge technology behind image recognition. From distinguishing cats from dogs to detecting anomalies in manufacturing processes, CNNs are at the forefront of AI. Image recognition tasks involve classifying objects within images. Whether it's distinguishing between cats and dogs or ensuring safety in robotic environments, the applications are vast. Even tasks like tagging friends in photos benefit from this technology. In computers, images are represented as pixels, with grayscale images consisting of values ranging from 0 to 255. Color images introduce additional channels such as RGB, encoding red, green, and blue values. Understanding these basics sets the stage for deeper exploration. In 2012, CNNs revolutionized image analysis, doubling recognition rates in a popular contest compared to previous technologies. This dramatic increase in performance is only possible due to a unique structure with specific hidden layers. So let's take a closer look at the specifics of such a convolutional neural network. We'll start with the input and output layers. In the case of a grayscale image, each pixel value corresponds to an input neuron. Our example image has 16 by 16 pixels, so there are 256 input neurons. The number of output neurons is determined by the number of classes. If the CNN is used to classify handwritten digits as numbers between 0 and 9, it will have 10 output neurons, one for each class. Then there are so-called convolution layers that extract relevant patterns such as edges, textures, or shapes, which are crucial for subsequent processing. Kernels of predefined size are used for feature extraction. These kernels slide over the input image and perform element-wise multiplication and summation operations. After adding a bias and applying the activation function, the resulting feature maps highlight the relevant patterns. The size of these feature maps depends on the kernel size and the stride length. So-called pooling layers reduce the spatial dimensions of the feature maps generated by the convolutional layer. By downsampling the feature maps, pooling layers reduce computational complexity and prevent overfitting. Common pooling operations include max pooling, which preserves the maximum value within a window. Again, the size of the pooled feature map depends on the kernel size and stride length. Fully connected layers allow the network to learn complex relationships between the extracted features and compute class probabilities. These layers connect the flattened feature map from the previous layers to the output layer. As we learned in our previous units, the neurons in these layers compute weighted sums of input values and apply an activation function to produce the final output. Training deep CNNs from scratch requires huge amounts of image data and computational resources. Transfer learning provides a solution by leveraging pre-trained networks for specific tasks. By fine-tuning pre-trained models on smaller datasets, practitioners can achieve remarkable performance with less time and computational cost. CNNs consist of different layers and can effectively tackle various image recognition tasks. But keep in mind that training CNNs can be time-consuming and expensive, so consider transfer learning. Stay tuned for more insights into the world of AI in our upcoming units. Until then, happy learning!